We're going to read through this lesson here from the packet. This is lesson 4.1 about the flow of electrical energy. And what we've got here is a picture of the filament of a light bulb. And you can see when you look at it here that especially right here, you can see that the filament is coiled like this. And that's going to be important later. We'll talk about that later. So let's read on here. It says an electric current in a thin metal wire can raise the metal's temperature until it glows. Can you explain this phenomenon? An incandescent light bulb, incandescent means, by the way, that it glows. An incandescent light bulb contains a thin wire called a filament that glows when there's enough electric current in the filament, and we're going to talk about what electric current is. The tungsten filament in a typical 100-watt incandescent bulb reaches temperatures over 2000 degrees C. Tungsten, by the way, is an element on the periodic table. Whoops, let me see if I can fix that. An element on the periodic table. It's a metal. A wire at this temperature would combust. That means it would burn up if it was exposed to oxygen. So the filament is encased, that is contained in a bulb, a glass bulb, filled with an inert gas. An inert gas is a gas that does not react, unlike oxygen. Incandescent bulbs are used in warming lamps and incubators where the energy released as heat is a benefit. When warming is not wanted, fluorescent or LED bulbs may be a more desirable choice of lighting. The reason for that is they use less electricity. So here's our first thing that it wants us to do, and you can find this in a Google form that I've put in Google Classroom. We're on page 241, and it says gather evidence. Can you think of any similar phenomena that could help explain why the filament glows when an electric current is in the wire? Similar phenomena are other things that happen. So, for example, we have been talking about electromagnetic radiation and waves, and we know that waves are produced when something is vibrating. I'm trying to make something vibrate, not a bunch of waves, but when something vibrates, we get waves that are produced. Waves maybe like this. Okay, so what might be causing vibrations in the light bulb? That's what we want to think about, and we're not going to worry about filling this one out right now. We're just going to keep reading, and we'll actually come back to this at the end of the chapter. So here's exploration 1, describing electrical energy. So we're going to need some words so that we can talk about electricity. One of the things we need to realize is that electrons are negatively charged particles that in certain materials can move, and this especially happens in metals. The movement of electrons is how electrical energy is transferred in a circuit. So there's another vocabulary word. Electrical energy is the form of energy associated with charged particles due to their positions and motions in an electric field. Like other forms of energy, electrical energy is measured in joules. Here is our second thing that we get to do on the Google form. It says infer. When a dimmer switch, this is a dimmer switch over here, by the way, this is what one kind of dimmer switch looks like. When a dimmer switch is lowered, the brightness of the light bulb decreases. How does the brightness of an incandescent light bulb relate to the rate of flow of the energy through the bulb? We could say maybe that brightness decreases when the rate of flow of energy decreases, or maybe brightness decreases when the rate of flow of energy increases, or maybe brightness decreases but the flow of energy remains the same. So think about it and pick one of those on the Google Doc. Using electrical energy. Like a mass in a gravitational field, a charge in an electric field, see, we have gravitational field and we have electric field, and they're related in interesting ways that we're not going to go into right now. A charge in an electric field experiences a force that would move it from a position of higher potential to a position of lower potential. We don't know what any of those things mean yet, but they're about to tell us. The electric potential difference between 2 points, voltage, is the amount of work needed to move a unit of electric charge between those 2 points. Voltage is measured in volts, and a volt is equal to 1 joule per coulomb. Now, a coulomb is a measurement of a number of electrons. Don't worry about that right now. When charged particles move due to an electrical potential difference, the electrical energy of the particles may be transformed into other forms of energy, like thermal, that is heat, or radiant, that is the production of electromagnetic radiation, or mechanical. People use these energy transformations to operate devices from toy cars to full-size electric vehicles, to light homes, or to entertain. Electrical energy may even be transformed into sound energy through electric speakers, or AirPods, or earbuds, or whatever. Though the energy in a battery is stored in chemical bonds, it is often described as electrical energy because it generates a voltage. So here in figure 2, it says electrical energy can be stored in batteries. Electric energy can be transformed into radiant energy, that's the light down here. And sound energy, I don't know if we can, that's probably a big speaker right there. That's a great big speaker. Sound energy. Radiant energy and sound energy as it is at a stage show for a music concert. We do not see appropriate physical distancing there. Bad, bad, very bad. Anyway, here are 2 AA batteries, and it says right here that each battery holds 1.5 volts of electricity. Now, they just told us that electric fields happen when electrons move. So we're going to learn about electron motion. And this is another thing to look at on the Google form. It says, argue. Metals have some electrons called free electrons that can move throughout the metal. How would one of these electrons move in a metal wire when there's no difference in electric potential across the wire? And by across the wire, they actually mean from one end of the wire to the other. So the choices are it would not move at all. Remember, there's no difference in electric potential across the wire. It would not move at all, so it would just stay in one place. It would remain in one atom, so maybe it moves, but only inside of just one atom. Or C, it would move throughout a metal, but stay in the same area over time. Or D, it would move continuously in one direction. Well, the way this book is set up here, it asks us a question, and then it gives us the answer to the question. So let's read that. Free electrons move quickly in different directions. And that's what we see here. Here's a free electron, and it's moving in different directions. I'm not going to try to trace it. What I am trying to do is draw what happens to an electron that is not in an electric field. Free electrons move quickly in different directions. When an electric field acts in the wire, the electron's average positions slowly drift in a direction aligned with the electric field. So here we have the drift velocity. Looking at the picture here we have the drift velocity is from the left to the right. That's because there is an electric field in this example. Up here, there's no electric field. Well, that didn't work very well. I was going to try to write no field. Down here, the black line shows an electron moving in an electric field, and the red line shows what the electron might do if there was no electric field. The strength of the electric field determines the drift velocity. A stronger electric field accelerates the free electrons more. Because all of the electrons in the electric field experience a force from the electric field, all of the free electrons drift in the same direction at the same time.